Welcome to Measurement System Analysis, also known as MSA. In manufacturing, engineering, quality control, and process improvement, almost every important decision is based on data. We measure product dimensions, weight, pressure, temperature, defects, inspection results, and many other process outputs. But before we trust that data, we need to ask one very important question. Is the measurement system itself accurate and reliable? Because if the measurement system is not working properly, then the data we collect may not represent the actual process. A good product may be rejected, a defective product may be accepted, or a stable process may look unstable just because of measurement error. This is why MSA is very important. It helps us understand whether our measurement system can be trusted before we use the data for quality decisions, process control, or improvement projects. So in this course, we will begin with the foundations of MSA. You will understand what a measurement system is, why data quality matters, and how measurement error can affect every decision you make. Then we will move into bias analysis, where you will learn how to check whether a gauge is consistently measuring higher or lower than a true reference value. Next, we will cover stability analysis, which helps us understand whether the measurement system remains consistent over time or starts drifting. After that, we will study linearity analysis, where we check whether a gauge is accurate across its full operating range, not just at one measurement point. Then we'll move into one of the most important areas of MSA, repeatability and reproducibility, commonly known as Gage R&R. Here you will learn how much variation comes from the measuring equipment and how much comes from the different operations using that equipment. We'll also explore the average and range method, the ANOVA method, and finally attribute gauge analysis for pass or fail inspection systems using cross-tabulation and Kappa statistics. So by the end of this course, you will understand how to evaluate measurement systems, identify sources of error, and improve the reliability of your data. So let's begin this learning journey and understand how MSA helps organizations make better, smart, and more confident quality decisions. Before we move into the video, let me give you a quick information. If you're serious about improving process, reducing errors, and making smarter business decisions, then this free Six Sigma course is a great place to start. It gives you a strong foundation in Six Sigma principles, process mapping, DMAIC methodology, and practical quality improvement concepts that professionals actually use in real projects. What makes this even better is that it's beginner-friendly, so you don't need to be an expert to get started. Whether you're from operations, project management, business analysis, or even just looking to build process improvement skills, this course can help you understand how organizations improve performance step by step. And the best part, you get access to a free learning experience along with a completion certificate, which can add value to your resume and show employers that you're building relevant industry skills. So if you want to go beyond theory and actually learn how Six Sigma helps teams work smarter, reduce waste, and improve quality, this is the right course to enroll in. So whether you're a quality engineer, product engineer, process engineer, quality analyst, or someone who wants to move into quality management, this course can help you build the confidence, technical understanding, and skills needed to validate measurement systems, make better quality decisions, and grow in your career. Don't just stop at understanding the concept. Take the next step and start learning it in a structured way. Hurry up and enroll now. The course link is given in the description box below. Hello everyone, welcome to this course on measurement system analysis. This course is structured with one goal in mind: to give quality engineers and professionals a practical, structured understanding of how to evaluate, validate, and improve the measurement systems they rely on every single day. Whether you work in automotive, aerospace, manufacturing, pharmaceuticals, or any other industry where quality matters, measurement system analysis is a skill that sits at the very core of reliable decision making. Yet, it is rarely given the depth it deserves. This gap is exactly what this course addresses. This course walks you through the complete framework of measurement system analysis, from the moment you question whether your data is trustworthy, all the way through bias, stability, linearity, gauge, R&R, and attribute inspection analysis. So let me give you a quick summary of the topics that will be covered in each module. So Module 1 introduces the foundations of MSA, which includes what a measurement system is, why data quality matters, and how measurement error affects every quality decision that you make. And Module 2 covers bias analysis, understanding systematic error, reference values, and how to test whether your gauge is telling you the truth. Module 3 covers stability analysis, how to detect drift in your measurement system over time using control charts and variation principles. And Module 4 covers linearity analysis, evaluating whether your gauge is equally accurate across its full operating range. Module 5 covers repeatability and reproducibility. These are the two dimensions of measurement precision and how a Gage R&R study is structured. Module 6 covers the average and range method. This is a traditional, transparent approach to calculating and interpreting Gage R&R results. Module 7 covers the ANOVA method. the more statistically rigorous approach that detects interaction effects and delivers more precise variance estimates. And Module 8 covers attribute gauge analysis, evaluating pass or fail inspection systems using the cross-tabulation methods and Kappa statistics. So in this video, we are going to go through the complete foundations of MSA, from what it means to bias, stability, linearity, repeatability, reproducibility, the average and range method, and all the way through attribute gauge analysis and Kappa statistics. So by the end of this course, you will understand the purpose and importance of MSA, that is measurement system analysis, in quality management. You will learn how measurement systems affect the product quality, process control, and decision making. You'll also understand how to evaluate whether a measurement system is reliable, consistent, and suitable for use in quality operations. You will learn how to identify measurement bias by comparing measured results with known reference or master values. You will understand what bias means, how it can affect inspection results, and how to determine whether the level of bias is acceptable for a given process or product requirement. You will know how to evaluate the stability of a measurement system over a period of time. You will learn how to use control charts to monitor measurement performance and identify unusual patterns, shifts, or trends. You'll also learn how to investigate possible causes of variation, such as equipment wear, environmental changes, operator differences, or calibration issues. You will understand how to use the average and range method to perform a gauge repeatability and reproducibility study. You will know how to calculate repeatability, reproducibility, total Gage R&R, part-to-part variation, and percentage contribution. You'll also learn how to interpret the results to decide whether the measurement system is acceptable, needs improvement, or is not suitable for use. You'll get a clear understanding on how the ANOVA method is used in Gage R&R studies to separate and analyze different sources of variation. You will learn how to identify variation caused by parts, operators, equipments, and operator-by-part interaction. You'll also understand how interaction effects are important and how they can indicate inconsistent measurement behavior between appraisers and parts. And finally, you will learn how to evaluate measurement systems used for attribute or judgment-based inspections, such as pass or fail, good or bad, or accepted or rejected decisions. You will understand how to assess agreement between appraisers, agreement with a standard, and consistency within appraisers. You will learn how to interpret Kappa statistics to determine the strength of appraiser agreement and the reliability of the attribute measurement system. Welcome to Module 1. So in this module, we will begin by understanding what a measurement system truly is, and not just the instrument, but the full combination of equipment, operators, method, environment, and parts. Next, we will explore why data quality matters, looking at how accuracy and reliability affect every quality decision that you make. We will then examine how measurement plays a role in both product control and process control before diving into the core concepts of bias, variability, accuracy, and precision. Finally, we will look at process capability, distributions, and how measurement error impacts hypothesis testing. Together, these concepts will give you a solid understanding of why reliable measurement systems are absolutely essential in any quality environment. So let's start at the very beginning. Measurement system analysis, or MSA, is a collection of statistical and analytical methods that is used to evaluate the quality and capability of a measurement system. The instrument or the gauge itself, the operator who used it, the method or the procedure followed, the environment in which measurements are taken, and the parts or samples being measured. All of these components contribute to the final measurement that you get, and all of them can produce error. The purpose of measurement system analysis is to understand and quantify that error, to figure out how much of what you're seeing in your data is real variation from your process or the product, and how much is just noise from your measurement system. Think of it this way. Imagine you're trying to listen to someone speaking across a noisy room. You can hear them, but there's a background noise. Some of what you hear is their voice, real signal, and some of it is just the noise of the room. MSA helps you figure out how much is the signal and how much is the noise. A good measurement system has low noise, and a poor measurement system drowns out the signal. The importance of a reliable measurement system cannot be overstated. Every quality decision, every product acceptance or rejection, every process adjustment, every capability study is only as good as the data behind it. And the data is only as good as the measurement system that produced it. So now let's understand the importance of data quality, because this is really the heart of why MSA matters. When we talk about the data quality in context of measurement, we are looking at two key dimensions: accuracy and reliability. Accurate data means your measurement system gives you something close to 25.03 and not 25.10 or 24.95. It has low bias and high accuracy. Inaccurate data leads to wrong confirmation decisions. Accurate data is the first dimension of data quality. Now let's understand about reliable data. Reliable data means that if you measure the same thing multiple times under the same conditions, you get consistent results. Reliability is about repeatability and stability over the time. Low variability has high reliability, and unreliable data leads to inconsistent decisions. Reliability is the second dimension of data quality. Now, what happens when the data quality is poor? The consequences are everywhere. First, bad decisions on product conformance. If your measurement system is inaccurate, you might pass parts that are actually defective or reject parts that are perfectly good. Both outcomes cost money. Shipping defective parts damages customer relationships and creates warranty issues. Rejecting good parts means wasted production and unnecessary rework. Next is flawed process control. If you're using measurements to monitor a process, drawing control charts, making adjustments, and your measurement system is unreliable, then your control charts are full of noise. You end up reacting to variation that isn't real, making adjustments that aren't needed, and missing signals that actually matter. Then comes misleading capability studies. Process capability indicates like CP and CPK are based on measurement data. If the measurements themselves carry significant error, your capability numbers are wrong. You might think your process is capable when it isn't, or think it's incapable when it's actually performing well. So in every case, poor data quality leads to poor decisions, and poor decisions have a cost in time, in money, in customer satisfaction, and in quality. And that's why MSA is a necessity for any serious quality system. Now let's look into product and process control. This is where measurement actually shows up in the real world of quality, specifically in product control and process control. Product control is about the individual units. You make a part, you measure it, and you decide, does this part meet specifications? Is it within tolerance, or you accept or reject? This kind of a decision sounds simple, but it depends entirely on the measurement system. If the measurement system has significant bias, you might be completely making the wrong call consistently. If it has poor repeatability, the same part might measure as a pass in one reading and a fail in the next. If your measurement system itself has a variability of plus or minus 0.04 mm, then a huge portion of your measurement spread is coming from the gauge and not from the part. So let's understand about process control. Process control focuses on how the process behaves over time, not just whether one individual part passes or fails inspection. Is the process continuously producing good parts? This helps identify whether the process is stable, predictable, and capable of meeting the requirements. Measurements are taken regularly. In process control, data is collected at plant intervals and plotted on control charts. These charts help us show normal variation versus unusual behavior. Patterns such as points outside the control limits, trends, runs, or cycles may indicate that something in the process has changed and needs attention. SPC depends on trustworthy measurements. Statistical process control, or SPC, uses data to monitor and improve process. However, SPC is only useful when the measurement system is reliable. If measurements are accurate, consistent, and repeatable, the control chart reflects the true condition of the process. Poor measurement systems cause false alarms. If the measurement system is unstable, the control chart may show signals that are not caused by the actual process. For example, a point may appear outside the control limits because of the measurement error and not because the process changed. This can lead to incorrect conclusions. False alarms waste resources. When false signals occur, teams may spend time investigating problems that do not really exist. This can lead to unnecessary adjustments, downtime, extra inspections, and wasted effort. In some cases, changing a stable process based on bad data can actually make performance worse. Measurement has two key roles. Measurement acts as a gatekeeper by helping decide whether the products meet requirements. It also acts as a monitoring tool by showing whether the process remains stable over time. If the measurement system is poor, both the product decisions and process control decisions become unreliable. So now that we've looked into product and process control, let's understand briefly about bias and variability, because these are the two most fundamental concepts in all of measurement system analysis. Bias is a consistent difference from the true value. Bias is a systematic error in a measurement system. It shows how far the average measured value is from the known reference value. If the measuring device consistently needs too high or too low, the system has bias. Let me give you an example. True diameter is 10 millimeters. Assume a pin has certified or known diameter of 10 mm. This value is treated as the reference or true value. The purpose of the measurement study is to see how close the gauge readings are to this known value. So measuring the same part multiple times, that is, when the same pin is measured 20 times, the readings may not all be exactly the same. Some may be slightly higher or lower. By taking repeated measurements, we can calculate the average reading and compare it with the reference value. So if the average of the 20 readings is 10.012 mm, then the gap is reading high by 0.012 mm. That is, bias is observed average minus reference value. So the difference you get is 0.012 millimeters. This means the gauge consistently overstays the diameter by 0.012 mm. So bias is repeatable error. It's not random scatter. It is a consistent shift in one direction. If the gauge is biased high, most measurements will tend to be higher than the true value. If it is biased low, measurements will tend to be lower. So the common causes of bias include, it can come from a worn or damaged gauge, poor calibration, improper zeroing, and incorrect master part of reference standard, or a measurement method that consistently pushes results in one direction. Variability is the amount of scatter in repeated measurements. Even when measuring the same part under the same conditions, the readings may vary slightly because no measurement system is perfectly precise. Bias moves in one direction, it is consistent offset. For example, a gauge may always read slightly high or always read slightly low. This affects the accuracy of the measurement system. Variability is different from bias because it does not always move in one direction. One reading may be high, another may be low, and another may be close to the average. This affects the precision of the measurement system. A good measurement system must be both accurate and precise. Low bias means the average is close to the true value. Low variability means repeated readings are close to each other. If either one is poor, measurement decisions become unreliable. So let me tell you the sources of variability. It can come from the instrument's precision, differences between operators, changes in temperature or humidity, part positioning, fixture setup, or unclear measurement procedures. Standardizing the method helps reduce this variation. Now let's talk about accuracy versus precision, because the distinction is cruel and it's often confused. So accuracy refers to how close your measurements are to the value. Low bias has high accuracy. And precision refers to how consistent your measurements are with each other. Low variability has high precision. Let me give you a classic illustration. So in this picture, the bullseye is a true value. Accurate and precise. This means all darts are tightly grouped around the bullseye. This means the measurement system is both correct and consistent. The readings are close to the true value and repeated measurements give nearly the same result. This is the ideal condition. The next is precise but not accurate. You can see here all darts are tightly grouped together but away from the bullseye. This means the system is consistent but wrong. The measurements repeat well but they are shifted from the true value. This usually indicates bias in the measurement system. Next is accurate but not precise. Here you can see that the darts are spread out but their average position is near the bullseye. This means the system has little or no bias at all, but it has too much variation. Individual readings are not reliable because they fluctuate too much from one measurement to the other. The last is neither accurate nor precise. Here the darts are scattered widely and away from the bullseye. This means the system is both inconsistent and wrong. It has poor accuracy and poor precision, making it unreliable for inspection, SPC or process decisions. A good measurement system needs both accuracy and precision. MSA gives you the tools to evaluate and improve both. So before we can evaluate whether a measurement system is good enough, we need to understand what it's being compared against, and that's where process capability and distribution comes in the picture. What is process capability? It's a statistical measure of how well a process can produce output within its specification limits. The most common capability indices are CP and CPK. CP looks at the overall spread of the process relative to the tolerance width. CPK also accounts for which the process is centered relative to the specification limits. A CPK of 1.33 or higher is generally considered acceptable in most industries. A CPK below 1 means the process is not capable. It's producing defects. But here's the key connection to MSA. Your capability numbers are only meaningful if your measured system is capable too. If your gauge contributes significant variation, it inflates the apparent spread of your process data. Your CPK looks worse than it really is, and you might launch an expensive improvement project on a process that was actually fine, while your measurement system was the real problem. So when we talk about the distributions in the context of MSA, we are usually thinking about the normal distribution, the familiar bell curve. In a stable, well-behaved process, measurements tend to follow a normal distribution. Understanding the shape and spread of your data distribution helps you see whether your measurement system is introducing distortion. A measurement system with poor precision borders the distribution. Bias shifts its left or right. Non-linearity might cause it to look skewed. Interpreting these distributions is a key skill in measurement system analysis. So now let's look into hypothesis testing and the impact of measurement error on statistical decisions. In quality engineering, we often use hypothesis testing to make decisions. Is process A better than process B? Has the process been shifted? Is there a difference between two measurement methods, etc.? Hypothesis testing works by setting up two competing claims. The null hypothesis, that is H0. There is no difference, no effect, and no change. The alternate hypothesis, H1, there is a difference in effect or a change. We then collect the data and use the statistics to decide which hypothesis in the data supports. But this process can go wrong in two ways. Type 1 error, also called as false positive or alpha error. This occurs when you reject the null hypothesis and when it's actually true. You conclude that there is a difference when there isn't one. In quality terms, this might mean stopping a process or launching an investigation when nothing was actually wrong. Next, we have type 2 error. This is also called as false negative or beta error. This error occurs when you fail to reject the null hypothesis when it's actually false. You miss a real difference. In quality terms, this might mean failing to detect a process shift or accepting bad products as good. Gage error increases both types of mistakes. When your measurement system has significant variability, it adds noise to your data. And that noise makes it harder to detect real signals. That is increasing type 2 error, but it also creates false signals, that is increasing type 1 error. The cost of gauge error is therefore not just a measurement quality problem, it's a decision quality problem. Every time your measurement system leads you to a wrong conclusion, there is a cost. Cost from unnecessary adjustment, from missed defects, from scraped good product, from failed audits. Now let's quickly look into hypothesis testing errors. Unnecessary process adjustment from false signals. A false signal occurs when the data suggests the process has only changed, but the change is only due to the measurement error or random noise. If the team reacts by adjusting the machine or process, they may disturb a stable system and create more variation. Missed effects from undetected real signals. Sometimes the measurement system fails to detect a real problem. A defective part may be accepted or a process shift may go unnoticed. This allows bad product to continue moving through the production, increasing the risk of rework, warranty claims, or customer dissatisfaction. Good product scrapped due to wrong measurements. If a measurement system reads incorrectly, good parts may be judged as defective. This leads to unnecessary scrap, wasted material, extra labor, and reduced productivity. The product was acceptable, but the wrong measurement decision created a loss. Failed audits and customer complaints. Poor measurement control can result in weak records, inconsistent inspection results, and unreliable quality decision. During audits, this may appear as a lack of control over the measurement system. Customers may also complain if defective products escape or if quality performance becomes inconsistent. Every wrong measurement decision has a financial cost. Incorrect measurements decision cost money. They can cause scrap, rework, downtime, extra inspection, delayed shipments, customer returns, and loss of trust. A reliable measurement system helps reduce these costs by supporting the correct decision in the first time. So with this, we have come to the end of this module. In this module, we covered the foundations of what a measurement system is. It's not just the instrument, but the complete combination of equipment, operators, method, environment, and parts. We explored how data quality depends on both accuracy and reliability, and how poor measurement systems leads to flawed product decisions, unreliable process control, and misleading capability studies. We also had a look at the critical concepts of bias, variability, accuracy, precision, and the impact of gauge error on hypothesis testing decisions. Welcome back. In this module, we go deep into one of the most important properties of a measurement system. That is bias analysis. We will take a focused look at bias, which is one of the most critical properties of any measurement system. We will begin by understanding what measurement bias is and what causes it and how it silently shifts your measurements away from the true value. Next, we will explore the concept of reference values and how they serve as the benchmark for evaluating gauge accuracy. We will then walk through the step-by-step process of testing for bias and learn how to interpret the results by expressing bias as a percentage of tolerance. Together, these concepts will give you a clear and practical approach to identify, evaluate, and act on bias in any measurement system. So now let's get started. Measurement bias is the difference between the observed average of measurements and the accepted reference value of the part being measured. In simple terms, how far off is your gauge on average? Bias is a systematic error. It is not caused by random variation. It is a consistent measurement error that pushes the result in one direction. Because it is systematic, repeated measurements do not cancel it out. Even if you measure the part many times, the average will still be shifted away from the true value. A biased gauge reads consistently high or low. A biased gauge may always show a value higher than actual dimensions, or it may always show a value lower than the actual dimension. For example, if a part is 10 mm, a biased gauge may repeatedly read around 10.012 mm. The readings may look consistent, but they are consistently wrong. So bias leads to wrong decision. If the bias is not detected, the measurement system gives false confidence. Good parts may be rejected, bad parts may be accepted, or process adjustments may be made when they are not needed. This is why bias is dangerous. It creates a pattern of reliable looking but incorrect decisions. So what causes bias? There are several common causes. The effect of bias on results is straightforward. It shifts your measurements away from the truth. And depending on which way the bias goes and how significant it is, it can lead to accepting out of specification parts or rejecting in specification ones. Worn or damaged instruments. A caliper with worn jaws, for example, will systematically give incorrect readings. Incorrect calibration. If a gauge is calibrated against an incorrect reference, every measurement it makes will be offset. Improper zeroing. If an instrument isn't properly zeroed before use, that offset carries into every measurement. Environmental factors. Temperature changes can cause materials to expand or contract, introducing bias if measurements are not taken at standard conditions. Operator technique. If an operator consistently applies too much or too little force when taking measurements, this can introduce a systematic bias. So to measure bias, you need something to compare against, and that's the reference value. Let's look into it. A reference value is also called a standard value or master value. It is a value that has been established with high precision and accuracy, typically using a higher level measurement system or a calibrated standard. Reference values are traceable. Reference values must be linked to recognized measurement standards through a documented calibration chain. This is called traceability. It means a reference value can be proven to come from a reliable source such as certified master part, calibration lab, or national or international standards like NIST in the United States. Reference value is the truth. The reference value acts as the accepted true value for comparison. When we measure a part with a gauge, we compare the gauge result to this reference value. The difference between the measured average and the reference value helps us determine whether the gauge has bias. When we take measurements of a reference part with our gauge, we get measured values. These are what the gauge actually reads. The difference between the reference value and the observed measurements, specifically the average of the observed measurements, is what tells us about bias. Let me give you an example. If the reference value is 50.00 millimeters and the average of 30 measurements taken with our gauge is 50.008 millimeters, the bias is plus 0.008 mm. Our gauge reads slightly high. It's important to understand that reference values are not perfect either. They have their own uncertainty, but they are established to be far more accurate than the gauge being evaluated. So for practical purposes, they serve as our true value. So how do we actually test for bias? Let's look into it. The process is conceptually simple. Though there are formal statistical procedures behind it, here's a basic approach. Step 1. Select a reference part. This is a part whose true value is known, measured using a higher accuracy, reference instrument, or calibrated standard. Step 2. Have a single experienced operator measure the reference part multiple times, typically 10 to 25 readings under normal measurement conditions. The operator should not know the reference value to avoid any conscious bias in the readings. Step 3. Calculate the average of all the measurements taken. And then calculate the bias. Bias is the average of measurements minus reference value. Statistically evaluate whether the bias is significant. This is typically done using a t-test, comparing the observed bias to the variability in the measurements to determine whether the difference could have occurred by chance. If the bias is statistically significant and practically meaningful, meaning it's large enough relative to the tolerance to affect decisions, then corrective action is needed. The bias study is not about finding zero bias. Some small amount of bias is almost always present. The question is whether the bias is small enough that it doesn't materially affect your measurement decisions. So once you've calculated the bias and run your statistical test, you need to interpret the results. Here's how that works. Bias expressed as a percentage of tolerance is the most practical way to evaluate it. You take the absolute value of the bias divided by the total tolerance range, then multiply by 100. The absolute value is used because bias can be positive or negative. But for acceptability, we care about the size of the error. If the tolerance is 0.10 mm and the bias is 0.008 mm, then the bias uses 8% of the tolerance range. An 8% bias means the gauge has a small consistent error compared with the total allowable variation. In many cases, this may be considered acceptable because the offset is not large enough to seriously affect product decisions. Expressing bias as a percentage makes it easier to compare different gauges, parts, and tolerance. A bias of 0.008 mm may be acceptable for a wide tolerance but unacceptable for a very tight tolerance. The percentage puts the bias into proper context. Bias percentage helps determine whether the measurement system is suitable for use. If the bias is too large, the gauge may reject good parts, accept bad parts, or mislead process control decisions. Lower bias means more reliable measurement decisions. But if the bias were 0.045 mm with the same 0.10 mm, then the tolerance that's 45%, nearly half the tolerance used up just by the bias in the measurement system. And that's clearly unacceptable. So now let's look into the guidelines for acceptability. If it's under 10%, it's generally acceptable. If bias is less than 10% of the tolerance, the measurement error is small compared to the specification range. The gauge is usually considered acceptable for normal inspection and process control use. If the bias is between 10 to 30%, it may be acceptable in some situations, but it should be reviewed carefully. The gauge may still be used for low-risk applications, but the improvement is recommended through calibration, repair, better fixturing, or improved measurement technique. If bias is greater than 30% of the tolerance, the measurement system is not reliable. The error consumes too much of the specification window, which can lead to wrong, accept or reject decisions. The gauge should be corrected before being used for product or process decisions. Acceptability depends on the risk. The final decision depends on the application. A low-risk feature with a wide tolerance may allow more measurement error. A critical safety, regulatory, or customer-sensitive feature requires a much tighter measurement system, even if the bias percentage appears moderate. If bias is found to be significant and unacceptable, the next step is to identify and eliminate the root cause. So this might mean recalibrating the instrument, repairing worn components, retraining operators, or revising the measurement procedures. If bias is acceptable, then you can document this and proceed with confidence that your measurement system is not introducing systematic error at a level that would compromise your decisions. So let's look into how to document bias results. Record the reference value, measurements, and average. Document the accepted reference value first. Then record every repeated measurement taken during the bias study. Finally, calculate and record the average of all the measurements. This provides the basic data needed to evaluate the gaps. Document bias and bias as percentage of tolerance. Record the bias value by subtracting the reference value from the observed value. Then express that bias as a percentage of the total tolerance. This shows whether the error is small or large compared with the specification window. Record the t-test result and conclusion. A t-test helps determine whether the observed bias is statistically significant or likely due to random variation. Record the test result, p-value if used, and the conclusion. Significant bias or no significant bias. State pass or action required. Clearly state whether the measurement system passed the bias study or needs correction. If action is required, identify the next steps such as calibration repair, method review, operator training, or replacement of the gauge. Retain the records. Keep all bias study records for audits, customer requirements, and future comparison. These records provide evidence that the measurement system was evaluated and help track whether the gauge performance changes over time. So with that, we have come to the end of this module. In this module, we covered how bias, a systematic directional error, silently shifts measurement away from the true value. We explored the concepts of reference values, how to conduct a structured bias test, and how to evaluate results by expressing bias as a percentage of tolerance. We learned that the bias below 10% is generally acceptable, between 10 to 30% requires judgment, and above 30% demands corrective action before the measurement system can be used reliably. Welcome back. In this module, we will explore how measurement systems behave over time, because a gauge that is accurate today may not remain accurate next month. We will begin by understanding what stability means and why drift in a measurement system can be just as damaging as bias. Next, we will look at how average and range control charts are used to monitor measurement performance over time and detect changes before they compromise your data. We will then explore the difference between common cause variation, which is expected and normal, and special cause variation, which signals a real problem that needs investigation. Together, these concepts will equip you to monitor, interpret, and maintain the long-term consistency of your measurement systems. So now let's get started. So far, we've talked about bias, which is a measurement of how accurate your gauge is at a specific point in time. But measurement systems don't exist frozen in time. They are used day after day, week after week in changing environments by different operators and with equipment that ages and wears. So let's look into stability. It is a property of a measurement system that remains consistent over time. A stable measurement system produces the same results today, next week, and next month or next year when measuring the same part under same conditions. So why does the stability matter? Because calibration is not forever. Even a perfectly calibrated gauge can drift over time due to mechanical wear, environmental exposure, or handling. A stability analysis tells you whether your measurement system is maintaining its performance over time or whether it's changing in ways that could compromise your data. The effect of instability on measurements is similar to bias, except instead of being a fixed constant offset, it's a changing one. An unstable system might be accurate today and significantly biased next month. Without stability monitoring, you won't know. So let's look into stability and drift. The primary concern in stability analysis is drift, a gradual systematic change in measurement output over time. Measurement drift occurs when the average reading of a measurement system changes progressively. This is different from random variability. Drift is directional and cumulative. Common causes of drift include mechanical wear. As instrument components wear down, readings change. Temperature effect. Instruments and parts expand and contract with temperature. A gauge used across different seasons or in a shop with varying temperatures may drift. Aging of electronics. Electronic sensors and circuits can change their characteristics over time. Contamination. Dirt, debris, or lubricants on contact surfaces can affect the readings. Operator fatigue or changing habits. Over long periods, operators may unconsciously change how they use a gauge. So now let's look into average and range chart concepts. The primary tool for conducting a stability analysis is the control chart, specifically the average bar chart and the range chart. Let me explain these concepts clearly. A control chart is a time series graph that displays measurement data over time along with statistical limits that define the expected range of normal variation. The average chart plots the average of a set of measurements taken at each time point. It monitors the central tendency of the measurement system, that is the average drifting over time. And the range chart plots the range, that is the difference between the highest and lowest reading of each set of measurements. It monitors the variability or spread of the measurement system, that is the consistency of the gauge changing over time, etc. Both charts have three lines. First is the central line, the average of all the plotted points. Next is the upper control limit, that is UCL, the upper boundary of expected normal variation. The lower control limit, that is the lower boundary. Control limits are typically set at plus or minus 3 standard deviations from the center line, which means that in a stable, normally distributed system, 99.73% of points should fall within these limits. So now let's understand about interpreting the charts. If the points within control limits and no unusual patterns, then it's a stable system. When all the points stay within the control limits and do not show abnormal patterns, the process is considered stable. This means the variation is mainly due to common causes or normal process variation. If it points outside the control limits, then that is a signal. A point outside the upper or lower control limit is a warning signal. It suggests that something has changed in the process and a special cause may be present. This should be investigated. Next, trends, runs, or cycles can show instability. Even if all the points are inside the control limits, patterns can still indicate a problem, a steady upward or downward trend. Long run on one side of the center line or repeating cycles may mean the process is changing. Sudden shift has special cause. A sudden jump or drop in the data often means something specific has changed, such as a new operator, machine adjustment, material change, tool wear, or environmental condition. Unusual variation is a process issue. Too much variation, too little variation, or inconsistent spread may indicate that the process is not behaving normally. This can point to the equipment problems, measurement issues, poor setup, or unstable operating conditions. Now let's understand the common cause and special cause variation. Understanding control charts requires understanding two fundamental types of variation, that is, common cause and special cause. Common cause variation is natural, inherent variability that exists in any measurement system or process. It's a background noise, that is a random, unpredictable fluctuation that comes from many small individual sources, each contributing a little to the overall variation. Common cause variation is expected. It's what a measurement system looks like when it's stable and operating normally. Points in a control chart that vary randomly within the control limits represent common cause variation. Next is special cause variation. This is also called as assignable cause variation, that is something different. It's a signal. It represents variation that comes from a specific identifiable source, that something that has changed, broken, or gone wrong. When a special cause is detected, the appropriate response is to stop and investigate. Find the assignable cause, fix it, remove it from the system. When only common cause variation is present, the appropriate response is not to make individual adjustments. That only adds more variability. Instead, if you want to improve the system, you need to make fundamental changes to the process or measurement system itself. Identifying unusual measurement behavior in a stability study is about distinguishing these two types of variation. If your measurement system is stable, you will see common cause variation. Special causes signal that something has changed and you need to find out what. Now let's interpret stability results. So how do you conclude a stability study? After collecting data over time, typically measurements of a reference part taken periodically over weeks or months and plotting them on control charts, you draw conclusions about whether the measurement system is stable or unstable. Stable measurement system. A stable measurement system gives consistent results over time. This means the variation seen in the data is normal and expected, not caused by a change in the gauge, operator, method, or environment. All points within control limits. On both the X-bar chart and R chart, all points should remain within the upper and lower control limits. This shows that both the measurement average and the measurement variation are under control. No non-random patterns. Even if all points are inside the control limits, the chart should not show unusual patterns such as trends, long runs, cycles, sudden shifts. These patterns may indicate that the measurement system is changing over time. Average and range remain consistent. The X-bar chart shows whether the average measurement is stable, and the R chart shows whether the spread or repeatability is stable. If both remain consistent, the measurement system is behaving predictably. Data can be trusted when the measurement system is stable. Measurements taken at different times can be compared with confidence. This means the data is reliable for inspection, SPC, process studies, and decision making. Now let's look into unstable measurement system. An unstable measurement system does not perform consistently over time. This means the data may be affected by special causes and may not reflect the true conditions of the part or process. One or more points outside the control limit indicates a signal that something has changed. This could be due to gauge damage, poor setup, operator error, environmental change, or calibration problems. A trend may show gradual wear or drift. A sudden shift may indicate a change in setup, operator, or calibration. A repeating cycle may suggest environmental effects such as temperature changes during the day. Average or variability changes over time. If the average measurement changes, the system may have bias or drift. If the range changes, the system may have repeatability problems. Either condition means the measurement system may not be reliable, so then the action is required. An unstable measurement system should be investigated before using the data for important decisions. Possible actions include recalibration, repair, operator training, method review, fixture improvement, or environmental control. This means the measurement system cannot be trusted to give consistent data over time. You need to identify the cause of the instability and correct it before relying on the data from the system. Use these results for improvement. Stability analysis doesn't just tell you pass or fail, it gives you diagnostic information. Drift the average points to bias developing over time, possibly wear or calibration drift. Increasing the range suggests worsening the precision, possibly wear or environmental issues. This information guides targeted corrective action. So in this module, we covered how measurement systems change over time through drift, wear, and environmental effects. We explored how average and range control charts are used to monitor measurement performance over time, and how to distinguish between common cause variation, which is expected and normal, and special cause variation, which signals something has gone wrong, and that must be investigated. A stable measurement system shows consistent, average, and ranges with no unusual patterns. So welcome to this module. In this module, we will examine linearity. There is a property that is closely related to bias, but with an important distinction. While bias tells you how accurate your gauge is at one specific point, linearity tells you whether that accuracy holds consistently across the full operating range. So we will begin by understanding what linearity means and why it matters in real measurement scenarios. Next, we will look at how bias is evaluated at multiple points across the range and how regression analysis is used to identify and quantify linearity error. Finally, we will explore how to interpret linearity results and decide whether your gauge can be used confidently across its entire range. Together, these concepts will help you evaluate measurement accuracy in a far more complete and practical way. So now, let's get started. So linearity is the consistency of bias across a full range of measurement values the gauge is expected to cover. So think about a ruler. Near zero, it might be perfectly accurate. But what if a larger value, say towards the end of the ruler, the markings are slightly off? You'd have a linearity problem. The gauge behaves differently at different points in its range. So why does linearity matter? Because most gauges are used across a range of values and not just at one specific measurement point. If the bias is different at low values versus high values, you can't simply correct for a single bias offset. The error changes depending on what you're measuring, which makes it much harder to account for. The effect of poor linearity on accuracy is that your measurements become unpredictably wrong, accurate in some parts of the range, inaccurate in others. And you may not even know which measurements to trust. So now let's understand about bias across the measurement range. The core concept in linearity analysis is understanding how bias varies across the measurement range. To study linearity, you need to evaluate the bias at multiple points across the range, typically at least 5 reference paths spanning from the low end to the high end of the gauge's operating range. So let's say you have a gauge with a range of 0 to 100 millimeters. You might evaluate a low reference part, that is perhaps around 10 millimeters. Next, a low middle reference part around 25 millimeters, a middle reference part around 50 millimeters, a high middle reference part around 75 millimeters, and a high reference part around 90 millimeters. For each reference part, you calculate the bias just as you would in a bias study by taking multiple measurements and comparing the average to the known reference value. Then you plot these bias values against the reference values. If the gauge is perfectly linear, all the bias values would be the same, meaning the gauge is equally accurate at all points in its range. But if the bias at low value is different from the bias at high value, if the data points show a trend or slope, then the gauge has a linearity problem. Now let's look into a reference value and measured value. The mathematical heart of a linearity analysis is the relationship between reference values and measured values. When you plot the bias at each reference value, you are essentially asking, is there a slope to this relationship? A perfectly linear gauge has a same amount of bias at every point in its measurement range. That means the gauge error does not depend on whether it is measuring a small value, a medium value, or a large value. The gauge may have some bias, but the bias remains constant. For example, suppose your gauge always reads 0.02 millimeters higher than the true value. In this case, the bias is the same at all reference values. When bias plotted against reference value, the graph also shows a horizontal line. This means the slope of the line is 0. A 0 slope indicates that the bias is not increasing or decreasing as the reference value changes. Therefore, the gauge is considered linear across its measurement range. A perfectly linear gauge can still be inaccurate if it has a constant bias, but its error pattern is predictable and uniform. A gauge has linearity error when the bias changes at different reference values. This means the gauge may be accurate at one part of the measurement range, but inaccurate in another part. The error is not constant across the range. Here, the gauge reads increasingly high as the reference value increases. The bias becomes larger at higher values. So in this case, the gauge reads too high at low values and too low at high values. The bias changes from positive to negative. When bias is plotted against reference value, the points form a line with a non-zero slope. A non-zero slope shows that the gauge error changes as the measured value changes. This is called linearity error. because the gauge does not behave consistently throughout its measurement range. So that's about reference value and measured value. Now let's understand how to identify linearity issues. So how to recognize a linearity problem in practice? Nonlinear measurement behavior shows up in a few ways. The bias is positive, that is, gauge reads high at low measurement values, but negative, gauge reads low at high values, or vice versa. Next, the bias increases consistently as measurement value increases. The bias is acceptable in middle of the range but unacceptable at the extremes. Each of these patterns has implications for how you use and correct the measurement system. The effect on measurement accuracy depends on where in the range your actual production measurements fall. If your parts are all in the middle of the gauge's range, where linearity is good, the problem may not affect you much. But if parts span the full range or if they fall in the region where the bias is largest, linearity error can significantly compromise your data. The impact on measurement decision is similar to bias. You may be accepting or rejecting parts incorrectly, but now the problem varies depending on the size of the part being measured. This can create confusing patterns where some measurements seem trustworthy and others don't. Now that we understood how to identify linearity issues, now let's understand what are the common causes of the linearity problems include. So, worn instrument mechanisms. Some gauges wear more at certain parts of their measuring range, especially near the extreme positions. As a result, the gauge may be accurate in the middle of the range, but give biased readings at the low or high end. A sensor should respond consistently as the measured value changes. If the sensor response is nonlinear, the error may increase or decrease across the measurement range. This means the gauge does not behave the same at all sizes. Improper calibration. If a gauge is calibrated at only one point but used across a wider range, it may appear acceptable at that point while still being inaccurate elsewhere. Multi-point calibration helps confirm that the gauge is accurate across the full operating range. Mechanical looseness. Loose parts, backlash, or poor fit in the measuring mechanism can affect readings differently depending on the position. This can create changing bias across the range and make measurements unreliable at certain points. Now let's understand how to interpret linearity results. Interpreting the results of a linearity study comes down to three things: the slope, the R-square value, which tells you how well the regression line fits the data, and the linearity percentage. Linearity percentage is calculated as slope into process variation by process variation into 100. Or more practically, it's often expressed as a percentage of the process variation or the tolerance that the linearity error represents. Acceptable linearity means a gauge has acceptable linearity when the bias remains nearly constant across the full measurement range. This means the measurement system performs consistently whether it is measuring low, middle, or high reference value. The gauge error does not increase or decrease significantly as the measured value changes. The slope of the bias versus the reference value plot should be close to zero. A slope close to zero indicates that there is a very little relationship between the reference value and the bias. In other words, the bias does not change much across the measurement range. The linearity percentage should also be small when compared with the tolerance or process variation. This means the amount of bias change is not large enough to significantly affect inspection or process decision. The regression line should appear relatively flat. A flat line shows the gauge behaves in a stable and predictable way across the entire range of measurement. The data points should also cluster close to the regression line. This indicates that the measurement results are consistent and that the variation in bias is not excessive. So overall, acceptable linearity means that the gauge can be trusted to measure parts accurately and consistently throughout its intended operating range. Now let's understand about unacceptable linearity. A gauge has unacceptable linearity when the bias changes noticeably across the measurement range. This means the gauge does not perform consistently at different reference values. It may be more accurate in one part of the range and less accurate in another part. The slope of the bias versus reference value plot is significantly different from zero. A clear positive or negative slope indicates that the bias changes as the reference value changes. A large linearity percentage indicates that the change in bias is too large compared with the tolerance or process variation. And when this happens, the measurement system may not be suitable for making reliable quality decisions. The regression line is not flat. Instead, it shows a clear upward or downward trend. This means the measurement error depends on the size of the part or reference value being measured. The bias values are clearly different at different points in the range. This shows that the gauge is not equally accurate across its full measurement range. Overall, unacceptable linearity means the gauge may give misleading results depending on where the measurement falls within the range. This can lead to incorrect acceptance or rejection of parts and may require calibration, adjustment, repair, or replacement of the measurement system. So if linearity is acceptable, you can use the gauge across its full range with confidence. If linearity is not acceptable, you have several options. Repair or replace the gauge. Restrict the gauge to only the portion of its range where linearity is acceptable. Apply correction factors at different parts in the range, though this adds complexity and introduces additional uncertainty. Recalibrate the instrument at multiple points across the range rather than just at one point. So with that, we have come to the end of this module. In this module, we covered how bias is not always consistent across the gauge's full operating range. We explored how linearity analysis evaluates bias at multiple reference points from low to high and uses regression analysis to determine whether bias changes as measurement value changes. A flat regression slope indicates good linearity, while a steep slope signals that the gauge behaves differently at different points in its range and cannot be uniformly trusted. Welcome to this module. In this module, we will dive into Gage R&R, the most widely recognized component of MSA. We will begin by understanding what Gage R&R means and how total measurement variation is split between the two-part variation and measurement system noise. Next, we will explore repeatability, the equipment variation seen when the same operator measures the same part multiple times, and reproducibility, the variation that arises when different operators use the same gauge on the same part. We will then look at how precision connects both of these concepts and how a Gage R&R study is structured using parts, operators, and trials to capture real-world measurement variation. Together, these concepts will give you a thorough understanding of how measurement system variation is identified, separated, and evaluated. Gage R&R stands for Gauge Repeatability and Reproducibility. It's a study that quantifies two key sources of measurement variation and helps you determine whether your measurement system is capable of distinguish between paths. Let me frame this clearly. In any set of measurement data, the total observed variation has two components: true part-to-part variation, that is the actual difference between parts, which is what you want to see; measurement system variation, the variation introduced by the gauge and the operators, which is noise. The goal of a Gage R&R study is to determine how much of the total variation is coming from the measurement system and whether that's acceptable. So together, they make up the total Gage R&R, which is compared to the total process variation or the tolerance to determine whether the measurement system is capable. So what is repeatability? Repeatability is the variation in measurements that is obtained with one measurement instrument when used several times by one appraiser while measuring the identical characteristic on the same part. So in other words, if the same operator measures the same part with the same gauge multiple times, repeatability is the variation in these readings. This is also called as equipment variation, that is EV, because it represents the inherent variation of the measurement instrument itself. So even if you hold everything else constant, same part, same operator, same condition, the gauge will give slightly different readings each time. That spread is repeatability. Repeatability is the variation in measurements when the same operator measures the same part using the same instrument under the same conditions. It shows how consistent the instrument is when everything else is kept as constant as possible. So what's the cause? Repeatability variation usually comes from the instrument itself. Even when the same person measures the same part repeatably, small difference can occur due to gauge resolution, internal wear, friction, looseness, poor contact, or limitations in the measuring device. So what would be the impact? Poor repeatability means the instrument does not give consistent readings. This makes it difficult to know whether changes in the data are caused by the actual part or by the measurement system. It can lead to wrong inspection decisions, false process signals, and unreliable SPC charts. So the goal is to keep repeatability variation as low as possible. A repeatable instrument gives nearly the same reading each time, making measurements more reliable for product acceptance, process control, and quality improvement. So the sources of repeatability variation include instrument resolution. Can the gauge even detect small differences? Mechanical variability. Tiny differences in how contact is made each measurement, part surface finish, or geometry. Parts that are rough or not perfectly round are harder to measure consistently. Environmental fluctuations, vibrations, air currents, etc. So you might wonder, why does repeatability matter? If repeatability is poor, it means that the gauge itself is inconsistent. Even a single skilled operator can't get consistent readings. That's a fundamental problem with the instrument, and not the amount of operator training will fix it. The instrument needs to be repaired, replaced, or reconsidered. The consistency of the same operator is the baseline test of instrument capability. Now let's look into reproducibility. Reproducibility is the variation of the average of the measurements made by different operators using the same gauge while measuring the same characteristic on the same part. This is called appraiser variation, AV, because it captures the difference between the operators. If operator A consistently measures a part as 25.02 millimeters and operator B measures the same part as 24.98 millimeters using the same gauge, the difference is reproducibility error. So the source of reproducibility variation include different grip or holding techniques, different speed or force of measurement, different visual interpretation of the reading, different levels of training or experience, different habits or methods that operators have developed over time. So the effect of the operator variation on the results can be significant. In industries where many different operators use the same gauge, incoming inspection stations, production floor, quality checks, reproducibility issues means that the acceptance or rejection of the parts depends on who is measuring and not just the part itself. That's not a fair or reliable system. The goal is for different operators to get the same results from the same part with the same gauge. Reproducibility studies identify when that's not happening. Now let's quickly look into precision in measurement. Let's connect these concepts back to the broader idea of precision. Precision is the degree to which repeated measurements of the same object under the same conditions give the same result. It's about consistency and not accuracy. Repeatability and reproducibility are both dimensions of precision. Repeatability is within operator precision. How consistent are measurements when the same person uses the same gauge on the same part? Whereas reproducibility is between operation precision. How consistent are measurements across different operators? Together, they define the precision of the measurement system. So the relationship between repeatability and precision is direct. Poor repeatability means poor precision at the most fundamental level. Even before you introduce multiple operators, if the gauge cannot give you consistent readings to a single operator, precision is compromised. So you might wonder why consistent measurements matter. In quality systems, consistent measurements are the foundations of consistent decisions. If two inspectors can't agree on whether part is good or bad, the inspection process is fundamentally unreliable. So the process control charts drawn from the inconsistent measurements are noise and not signal. Capability studies based on imprecision data are meaningless. Precision, through good repeatability and reproducibility, is non-negotiable for a capable measurement system. Now that you understood precision, now let's understand how Gage R&R study is actually structured. A typical Gage R&R study involves three key elements. A set of production parts is selected to represent the full range of a process variation. Typically, 10 parts are used. These paths should span the expected spread of the process from low to high. So the study captures how the measurement system performs across that range. Next is operators. Multiple operators, typically 2 or 3, are selected. These should be the actual operators who use the gaps in normal production and not specially trained measurement technicians. The goal is to capture real-world variation. Next is trials, that is replicates. Each operator measures each part multiple times, that is typically 2 or 3 times. These repeated measurements on the same part by the same operator are used to calculate the repeatability. Let's look into the sources of measurement variation. Repeatability. It is the variation that occurs when the same operator measures the same part multiple times using the same gauge. So it shows how consistent the gauge is under the same measurement conditions. Whereas repeatability reflects variation caused by the equipment itself, such as gauge resolution, fixture or setup condition, measurement method, instrument wear, environmental effects, and small differences in how the reading is taken. Low repeatability variation means that the gauge gives consistent results when the same person repeats the measurement. High repeatability variation means that the measurement system is not stable even under the same conditions. So this suggests that the gauge, method, or setup may need improvement. Reproducibility is the variation that occurs when different operators measure the same parts using the same gauge. So it shows how consistent that measurement system is between the operators. Reproducibility mainly reflects variation caused by differences in how operators perform the measurement, such as measurement technique, part positioning, reading interpretation, applied pressure or handling. Low reproducibility variation means different operators obtain similar measurement results. High reproducibility variation means operator technique or interpretation is affecting the measurement results. This may indicate a need for better training, clear instructions, improved fixtures, or a more standardized measurement method. The third is operator by part interaction. Operator by part interaction occurs when the difference between operators is not the same for every part. This means one operator may measure certain parts differently than another operator, and that difference changes depending on which part is being measured. This type of variation is important because it shows that the operator effect is not consistent across all the paths. So the ANOVA method can detect this interaction because it separates the variation into more detailed sources. It can show whether the measurement difference are due to only the gauge or only the operators or to the way specific operators measure specific paths. So when operator by part interaction is present, it may suggest that the measurement method is difficult to apply consistently across the full range of paths. It may also indicate that the part shape, surface condition, size or measurement location affects how operator take the readings. The result is a picture of how your measurement system's variation is distributed across these sources and how that compares to the total variation you care about. So with that, we've come to the end of this module. So in this module, we covered two core dimensions of measurement precision: repeatability, which captures equipment variation within a single operator, and reproducibility, which captures variation between different operators. We explored how a Gage R&R study is structured using multiple paths, multiple operators, and multiple trials to separate and quantify both sources of variation, giving a complete picture of how much of the total observed variation comes from the measurement system itself. So welcome to this module. Now that we understood the concepts of Gage R&R in the last module, let's look at the first and most traditional method for calculating it. That is the average and range method, also called as X bar and R method. In this module, we will walk through the average and range method, that is the traditional and most transparent approach to calculate the Gage R&R results. We will begin by understanding the purpose of the method and how it partitions total measurement variation into its key components. Next, we will explore how repeatability variation is calculated from the ranges of repeated measurements and how reproducibility variation is derived from the differences between the operator averages. We will then look into how these are combined into a total Gage R&R value and how much percentage is interpreted against the AIAG acceptability guidelines of under 10%, 10 to 30%, and over 30%. Together, these concepts will give you a clear and practical method for evaluating whether your measurement system is capable of supporting reliable quality decision. This method has been used for decades in the industry, and it's particularly valued for its simplicity and transparency. The calculations can be done by hand and the logic is very easy to understand. Let's get into it. So the purpose of the method is to partition the total measurement system variation into its components, repeatability and reproducibility, using basic statistics, averages, and ranges. The basic concept is this: by calculating the range of repeated measurements by the same operator on the same part, you get a measure of repeatability. By calculating the variation in operator averages, you get the reproducibility. Combine them and you have total Gage R&R. So let's understand about the average and range method. The average and range method is a common method used in Gage R&R study. It separates the total measurement variation into two main parts: repeatability and reproducibility. This helps identify whether the variation is coming from the instrument itself or from the difference between the operators. So this method breaks down the overall measurement system variation into smaller sources. The main focus is to determine how much variation comes from the gauge and how much comes from the people using the gauge. It uses averages and ranges. The method uses the average of repeated readings and the range between these readings. These values are used to estimate measurement variation and calculate the total Gage R&R value. Repeatability. Repeatability is calculated from the range of repeated measurements taken by the same operator on the same part. A large range means the instrument is not given consistent readings even when the operator and part remains the same. Whereas reproducibility, it is calculated from the variation in the average readings between the operators. So if different operators get different average results on the same parts, the measurement method may not be clearly defined or consistently followed. It is simple and transparent. The average and range method is popular because it is easy to understand and can be calculated by hand. It does not require complex software, making it useful for training, studies, and basic measurement system analysis. So the purpose of this method is to determine whether the measurement system is acceptable. A good system has low repeatability and reproducibility variation, meaning that the gauge is consistent and different operators get similar results. Now let's look into repeatability variation. So in the average and range method, repeatability or equipment variation is estimated from the ranges of repeated measurements. So here's the logic. If operator A measures part 1 3 times and gets 24.98, 25.1 and 25.0, the range of these measurements is 25.01 minus 24.98, that is 0.03 millimeters. That range reflects how much the gauge varied across these measurements of the same part by the same operator. You calculate this range for every combination of operator and part. Then you average all of these ranges to get the overall average range called R bar. So from R bar, using a statistical correction factor, you calculate the standard deviation of the equipment variation. And from the standard deviation, you calculate the equipment variation. This number, that is EV, represents the spread of repeatability variation in the measurement system. The effect on measurement consistency is direct. A high EV means the gauge is inconsistent even in the hands of a single skilled operator. Now let's look into reproducibility. Reproducibility or appraiser variation is calculated from the differences between the operator averages. The idea here is simple. After each operator has measured all the parts, you calculate each operator's overall average measurement. Then you look at the range of these operator averages, the difference between the highest and lowest operator average. This range combined with the correction factor gives you the standard deviation of appraiser variation, where n is the number of parts and r is the number of trials. This correction removes the contribution of equipment variation from the reproducibility calculation. The impact on measurement results of high AV is that different operators are consistently reaching different conclusions about the same paths. Now let's look into total gauge R&R. Total gauge combines repeatability and reproducibility into a single measure of total measurement system variation. So the formula is shown here, that is GRR is equal to under root of EV square plus AV square. This is a quadrature sum and not a simple addition because EV and AV are independent sources of variation and variances add, not standard deviations. GRR represents the total spread of variation introduced by the measurement system, both from the equipment and from the operators. So why does this matter? Because GRR is compressed to either the total process variation or the tolerance to determine whether the measurement system is capable. Now let's look into total variation. This is TV is equal to under root GRR square plus PV square, where PV is the part variation, that is the real variation between the parts in the study. The ratio GRR by TV expressed as a percentage tells you what fraction of the total observed variation is measurement system noise. The lower this percentage, the better the measurement system. Now we get to the question everyone wants answered. Is my measurement system good enough? In the average and range method, the primary metric is the percentage of GRR, that is the gauge R&R as a percentage of total variation or tolerance. So the AIAG guidelines for acceptability are: if it is under 10%, the measurement system is generally considered acceptable. 10 to 30%, the measurement system may be acceptable depending on the application, importance of the measurement, cost of the improvement, and other factors. So engineering judgment is required. Over 30%, the measurement system is not acceptable and needs improvement before it can be used reliably. So the number of distinct categories, that is NDC, is another important metric. It tells you how many distinct groups within the process variation the measurement system can distinguish. An NDC of 1 or 2 means the gauge can barely tell parts apart. An NDC of 5 or more is generally considered acceptable. So the formula is here, NDC equal to 1.41 into PV by GRR. Now let's look into how to make the decisions based on these results. If percentage GRR is under 10% and NDC is 5 or more, document and proceed. Your measurement system is capable. If results fall into 10 to 30% zone, weigh the cost of the improvements against the risk of measurement error in your application. High-risk applications, safety and regulatory demand better systems. If percentage GRR exceeds 30%, improvement is necessary. Identify whether the primary issue is repeatability, that is equipment, or reproducibility, that is operators. Target the largest contributor first. So with that, we've come to the end of this module. In this module, we cover the traditional average and range method for calculating gauge R&R, a transparent and calculable approach that partitions total measurement variation into equipment variation and appraiser variation. We explored how percentage GRR is calculated and interpreted against the AIAG acceptable guidelines under 10% acceptable, 10 to 30 marginal, and over 30% unacceptable, and how the number of distinct categories tells you whether a gauge can meaningfully distinguish between the paths. Welcome to this module. In this module, we will look into ANOVA, a more statistically powerful approach to gauge R&R analysis that goes beyond what the average and range method can offer. We will begin by understanding what ANOVA means and why it is valuable in measurement system analysis. Next, we'll explore the key sources of variations that ANOVA identifies: paths, operators, and measurement error, and then examine the concept of operator by part interaction, which the average and range method cannot detect. We'll also compare the two methods directly to understand when and why ANOVA is preferred choice. Finally, we'll walk through how to interpret ANOVA results and draw actionable conclusions. Together, these concepts will give you a more precise and complete tool for understanding where measurement variation truly comes from. ANOVA is a statistical technique that partitions the total variation in a dataset into components attributable to different sources. In this case, parts, operators, and measurement error. So the use of ANOVA in MSA allows us to break down variation in a more rigorous and complete way than the average and range method. It uses all the data more efficiently, provides more precise estimates how variation components, and critically, it can detect and quantify interaction effects between operators and parts. So why variation analysis matters? Understanding where variation comes from is the key to fix it. If most of your measurement system variation comes from the equipment, you need a better gauge. If it comes from the operators, you need training or procedure improvement. ANOVA tells you exactly how much each source contributes. So let's look into source of variation. In an ANOVA-based Gage R&R, the total variation in the measurement data is partitioned into these components. So the first is part variation. That is the genuine difference between the parts in the study. This is the variation you want your measurement system to be able to detect. High part variation relative to GRR is a good sign. It means you can distinguish parts from each other. Operator variation, the systematic difference between operators. This is a reproducibility component. Each operator has a characteristic average reading that differs from others. Measurement error, the residual variation that can't be attributed to either parts or operators. This is pure repeatability, the equipment variation within operators and within parts. ANOVA calculates a mean square for each source, which is a variance due to that source, and uses F-tests to determine whether each source is statistically significant. So why does this matter? By quantifying each source, ANOVA gives you a precise picture of where your measurement system variation is coming from and how much each source contributes. This guides targeted improvement action. So here's where ANOVA really shines over the average and range method, the ability to detect and measure interaction effects. An operator-part interaction exists when the difference between the operators is not consistent. In other words, operator A might measure some parts higher than operator B, but on the other parts, the relationship flips. So this kind of interaction can't be detected by the average range method. It just averages everything together and you can miss this subtly. So you might think, why does interactions matter? Because if operators measure parts differently depending on which part it is, the problem is more complex than simple operator bias. It might indicate that the measurement method is ambiguous. Different operators interpret the measurement procedure differently depending on the part's shape or size. Or it might indicate that some operators are better at measuring certain types of parts. Identifying interaction effects is important because the remediation is different. Training can fix a consistent operator bias, but operator-by-part interaction often requires clarifying or standardizing the measurement procedures so all the operator handle all parts consistently. So the effect of interaction measurement results is undetected interactions inflate the apparent repeatability error in the average and range method, giving you a misleading picture of where the problem lies. ANOVA separates it out, giving you a truer picture. Now let's look at the difference between ANOVA and average and range method. So the key difference is the average and range method is simpler and can be done by hand. It's been a standard in many industries for decades, but it has limitations. It doesn't detect interactions and it's less efficient in its use of data. ANOVA is more complex. It requires statistical software or sophisticated spreadsheet, but it uses all the data more efficiently and provides more precise estimates. It detects interactions and gives you formal hypothesis tests for each source of variation. Now let's look into advantages of ANOVA. It detects operator-by-part interaction. ANOVA can identify whether different operators measure certain part differently. This is called operator-by-part interaction. For example, operator A and operator B may agree on most parts but not on parts with a difficult shape or surface condition. So the X bar and R method may miss this, but ANOVA can detect it. It provides formal significant tests. ANOVA gives statistical tests for each source of variation. It can show whether variation is mainly coming from the part, the operator, the gauge, the interaction between operator and the part. This makes the analysis more objective and easier to justify. ANOVA estimates each component of variation more precisely. This is especially useful when the sample size is small or when the measurement decision is important. Better estimates help determine whether the measurement system is truly acceptable. This works better with unbalanced decisions. In real studies, data may not always be perfectly balanced. One operator may take fewer readings or one may have missing measurements. ANOVA can handle these situations better than the X bar and R method, making it more flexible. So you might wonder when to use ANOVA for detailed analysis. When operator by part interaction is suspected, use ANOVA when using operator may not measure all the parts in the same way. This can happen when parts are difficult to position, have complex geometry, or require judgment during the measurements. Use it when decisions are high at risk. ANOVA is preferred when measurement results affect safety, customer acceptance, regulatory compliance, or expensive production decisions. In these cases, a more rigorous method gives better confidence. Use when software is available. Modern statistic software makes ANOVA easy to perform. Since the calculations are handled by software, there is little reason to avoid ANOVA when detailed results are needed. Use when working in regulated industries. Industries such as medical devices, aerospace, automotive, and defense often require strong evidence that measurement systems are reliable. ANOVA provides a more detailed and statistically defensible analysis. So the main benefit is ANOVA gives you a deeper understanding of the measurement system. It not only estimates Gage R&R, but also explains where the variation is coming from and whether these sources are statistically significant. So let's see how to interpret ANOVA results. A typical ANOVA output for a Gage R&R study shows the source. The source of variation, that is parts, operators and part interaction, repeatability or error. Sum of squares, total variation attributed to each source. Degrees of freedom, the number of independent pieces of information. So now let's identify major sources of variation. If the parts contribute the most, then it's good. Your gauge can distinguish the parts. If repeatability is the largest component, equipment issue. That is, then you should investigate the gauge. If reproducibility is the largest, it's operator issue. Investigate training and procedures. If interaction is significant, procedure ambiguity. Clarify the measurement method. So apply the same acceptability guidelines as the X bar and R method. Percentage ERR under 10% is acceptable, 10 to 30 is marginal, over 30 is unacceptable. And act on the specific source that contributing most of the problem. So with that, we've come to the end of this module. So in this module, we covered the most statistically rigorous ANOVA approach to Gage R&R analysis, which goes beyond the average and range method by detecting and quantifying operator by part interaction effects. We explored how ANOVA partitions total variation into parts, operators, interaction, and pure measurement error, and how the resulting variance components guides targeted improvement, whether the issue lies with the equipment, the operators, or ambiguous measurement procedure. Welcome to this module. In this module, we will shift our focus to a completely different type of measurement system, that is attribute gauges, which produce pass or fail decisions rather than numerical values. We will begin by understanding what attribute measurement systems are, where they are used, and the unique types of errors they introduce. Next, we will explore attribute gauge error, including how incorrect classifications and appraiser disagreements occur on the impact they have on inspection reliability. We will then walk through the cross-tabulation method as the primary tool for evaluating attribute system performance before introducing Cohen's Kappa for 2 appraiser studies and Fleet's Kappa for studies involving 3 or more appraisers. Together, these concepts will give you a complete framework for evaluating and improving the reliability of any attribute inspection system. So everything we've discussed so far has been about variable measurement, where you get a numerical value. Attribute measurement is different. Instead of a number, you get a category, typically pass or fail, good or bad, yes or no. Visual inspection and classification-based inspections are all attribute measurement systems. Attribute gauges are used everywhere. Incoming inspection of visual features, surface finish assessment, color matching, defect classification. In many industries, attribute inspection is the primary type of quality control used. But attribute systems have their own source of error and they require their own analysis methods. Attribution inspection is used when the result is a category and not a measured number. Examples include pass or fail, good or bad, present or missing, or acceptable or not acceptable decisions. Since the inspector is making a judgment, the inspection system may be checked for consistency and accuracy. Good part classified as bad is a false rejection. The product actually meets requirements, but the inspection system rejects it. This can lead to unnecessary scrap, rework, extra inspection, delayed production, and higher cost. Bad part classified as good part is a false acceptance. This product does not meet the requirement, but the inspection system accepts it. This is usually more serious because defective product may reach the customer, causing complaints, returns, warranty claims, or safety risk. Both the errors have cost. False rejection wastes good product and production resources. False acceptance allows defective product to escape. Both reduce confidence in inspection process and can damage the customer trust. Attribute gauge analysis measures how far inspectors agree with the known standard and with each other. It helps determine whether the inspection method is reliable enough for the use. The goal is to confirm that pass or fail decisions are accurate, repeatable, and reproducible. A reliable attribute inspection system correctly accepts good part and rejects parts with a minimal error. Now let's look into attribute gauge error. It comes from incorrect classification, calling something good when it's bad or bad when it's good. Incorrect classification is a fundamental error in attribute inspection. Unlike variable measurement, where you can calculate a deviation and determine exactly how far you are, attribute errors are binary. You're either right or wrong. Appraisal disagreement is a key manifestation of attribute gauge error. If two inspectors look at the same part and one says pass while the other says fail, that's a disagreement. If the same inspector look at the same part on two different occasions and gives a different answer, that's also an error. The sources of appraisal disagreement in attribute system includes poorly defined acceptance criteria. If the standard for acceptable is vague or subjective, different inspectors will interpret differently. Inadequate training. Inspectors who haven't been well trained on what to look for. Visual fatigue. Inspectors who become less consistent over a long shift. Lighting and environmental conditions. Inconsistent inspection environments lead to inconsistent results. The impact of attribute error is significant. In high volume inspections, even a small error rate means large numbers of misclassified parts. And in safety critical applications, false acceptance can have serious consequences. Now let's look into cross-tab method concept. The primary analytical tool for the attribute gauge studies is the cross-tabulation method. It's also called the agreement table or confusion matrix approach. So here's how it works. Each appraiser inspects each part multiple times, typically 2 or 3 times, and then classifications are recorded. The results are then tabulated in a table that shows for each part what each appraiser decided and whether different trials by the same appraiser agreed with each other. Agreement table allows you to see how often each appraiser agrees with themselves, that is, within appraiser consistency, how often appraisers agree with each other, between appraiser agreement, and how often appraisers agree with the known correct answer. If a reference standard is available, this is appraiser accuracy. Comparison of appraiser decisions is done across all the parts in all the trials. The percentage of agreement, the proportion of cases where classification match, is the basic output. However, simple percentage agreement has a limitation. It doesn't account for the agreement that would occur by chance alone. If appraisers were randomly guessing, they'd agree some of them. This is where Kappa statistics come in. Cohen's Kappa is a statistical measurement that quantifies the level of agreement between two raters beyond what would be expected by the chance. So the formula is here. Observed agreement minus expected agreement by 1 minus expected agreement, where observed agreement is the actual proportion of cases where the two raters agreed, and expected agreement is the proportion of agreement you'd expect if both the raters were choosing at random based on their marginal rates. So by subtracting out the expected chance agreements and standardizing, Kappa gives you a measurement that range from 1, that is perfect agreement, to agreement no better than chance, and negative values, that is agreement worse than chance. So let's interpret Kappa results. 0.9 to 1 is excellent agreement, 0.7 to 0.09 is good agreement, and 0.5 to 0.7 is moderate agreement, may be acceptable depending on the stakes. So below 0.5 is a poor agreement. The attribute inspection system is not reliable. Cohen's Kappa is used when you have exactly 2 appraisers. For more than 2, you need fleece Kappa. When you're evaluating agreement among 3 or more appraisers, Cohen's Kappa doesn't directly apply. This is where fleece Kappa comes in. Fleece Kappa is a generalization of Cohen's Kappa that measures the overall level of agreement among multiple raters simultaneously. So instead of comparing pairs of raters, fleece Kappa looks at the distribution of ratings across all the raters and calculates single overall agreement statistic. The key differences between Cohen's and fleece Kappa is that Cohen's Kappa applies to exactly 2 raters. It's a pairwise comparison. Fleece Kappa applies to any number of raters. It's an overall measure across all the raters simultaneously. So in a real-world attribute gauge study with 3 inspectors, you would calculate fleece Kappa to get an overall picture of how well the team of inspectors agrees. Interpretation follows the same general guidelines as Cohen's Kappa values. Above 0.9 indicate excellent agreement, below 0.5 indicate poor reliability. Both are used to make a pass or fail judgment about the attribute inspection. If Kappa values are high, the inspection system is considered reliable. If Kappa values are low, the inspection process needs an improvement through better standards, better training, better lighting, or clear acceptance criteria. So with that, we've come to the end of this module. We covered the evaluation of attribute measurement systems, those that produce pass or fail decisions rather than numerical values. we explored how classification errors occur, how the cross-tabulation method is used to assess appraiser agreement, and how Cohen's Kappa and Fleet's Kappa measures agreement beyond the chance. A Kappa value above 0.9 indicates an excellent attribute inspection system, while value below 0.5 signals that the system is unreliable and requires immediate improvement. So now let's have a summary. Measurement systems are not perfect. Every measurement you take contains one error. The question is not whether error exists, but whether it's small enough to allow reliable decisions. Measurement system analysis gives you the tools to quantify that error. Through bias analysis, you can check the accuracy. Through stability analysis, you check consistency over time. Through linearity analysis, you check accuracy across the operating range. Through Gage R&R, you check repeatability and reproducibility. Through attribute analysis, you check classification reliability. The goal is trustworthy data. All the statistics, all the charts, all the indices, they serve one purpose: to tell you whether you can trust your measurement data. And if you can't, to tell you why so you can fix it. Next, MSA is not a one-time exercise. Measurement systems changes over time. Equipment wears, operators change, environments shift. Regular monitoring through stability analysis and periodic reevaluation of Gage R&R keeps your measurement system performing as required. The importance of MSA in quality system is, in Lean, Six Sigma and any serious quality measurement system, MSA is a foundational step before any data-driven analysis. So before you run a capability study, verify your measurement system. Before you draw conclusions from a control chart, make sure your measurement system is stable. Before you make a go or no-go decision, make sure your inspection system is reliable. Measurement is the window through which you see your process. If the window is dirty or destroyed, everything you see through it will be wrong. So now let's do a brief recap of what we have covered. In this course, we covered the foundational concepts of bias and variability all the way through sophisticated ANOVA-based Gage R&R and Kappa statistics for attribute systems. In Module 1, we introduced the foundations of MSA, what a measurement system is, why data quality matters, and how measurement error impacts product decisions, process control, and hypothesis testing. In Module 2, we covered bias, the systematic error, the measurement system, how to detect and test it using reference values, and how to evaluate its acceptability relative to tolerance. In Module 3, we address stability, how measurement systems drift over time and how to monitor and detect that drift using control charts and principles of common special cause variation. In Module 4, we explore linearity, whether a gauge is equally accurate across its full operating range and how to evaluate, interpret, and act on linearity results. In Module 5, we went into repeatability and reproducibility. These are the two dimensions of measurement precision, and how a Gage R&R study is structured to capture real-world measurement variation. Module 6, we walked through the average and range method, the traditional approach to calculating Gage R&R and how to interpret percentage GRR and number of distinct categories against acceptability guidelines. In Module 7, we looked to the ANOVA method, that is the more rigorous approach that detects operator by part interactions and it delivers more precise variance estimates. And finally, in Module 8, we concluded with attribute gauge analysis covering classification errors, cross-tabulation method, Kappa statistics for evaluating inspection system reliability. Now, as we come to the end of this course, let us briefly recap what we have covered. We have looked into the core principles of measurement system analysis and understood how MSA helps us evaluate whether a measurement system is accurate, consistent, stable, and reliable for quality operations. We also learned how MSA-driven analysis helps quality teams separate true process variation from measurement noise. This is important because quality decisions should be based on actual process performance and not errors or inconsistencies in the measurement system. By using reliable measurement data, teams can make stronger, data-backed decisions. We then covered structured Gage R&R studies and capability analysis, which help identify opportunities for improvement in the measurement system. These studies support continuous improvement by showing whether the system is suitable for use and whether it can provide reliable results over the long term. We also discussed the role of human oversight in measurement decisions. Even with strong MSA results, trained appraisers, clear inspection criteria, and responsible judgment are essential to ensure fair, consistent, and confident accept or reject decisions across product and process control. Finally, we looked at the importance of calibration practices, reference standards, and ethical use of measurement data. Strong calibration and reliable standards help build trust in measurement results, while ethical handling of data helps maintain quality system integrity and confidence in decision making. You now have a complete practical framework for evaluating, validating, and improving measurement systems, from understanding the foundations of data quality all the way through bias, stability, linearity, Gage R&R, and attribute inspection analysis. Thank you for completing this course. We wish you every success in applying these skills to your engineering projects. If you like this video, do hit the like button and subscribe to Simplilearn for more such videos. Thank you for watching. Until next time, keep learning with Simplilearn.